So what we're going to do today is go put the material together and go through three ways of understanding how the action potential is generated, which is, after all, the purpose of the ion channels. We're going to do this first in a way that's very descriptive, but which is sort of a catechism that most people have when you go through a standard biology or physiology textbook. Secondly, we're going to use a method that takes a graph theory way of understanding it. It gives you a lot of intuition of what's going on. And then thirdly, we're going to build up how you use numerical integration, something that you've seen in the past but may not have fully recognized the gusto of which, to simulate the action potential to the degree of precision that you desire. So there'll be a lot in this. Hopefully it'll be worth your while. So here's a neuronal action potential. Transmembrane voltage goes up, comes back down a little bit, lasts about a millisecond. And some of these subsidiary curves are some of the underlying currents that you want to expect to be in there. You'll remember from our previous lectures the dance of sodium and potassium currents shifting the target voltage, driving the cell towards the target in a sort of very smooth way to generate these spikes, so to speak. And the general way of explaining this is to come to our circuit diagram and give a little bit of a verbal scenario of what's going on. So at rest, which is out here, at rest, the main dominant conductance, although it's not a very big conductance, but the dominant conductance is that of the potassium current. So the equivalent circuit is something like this. So as we talked about, at rest, the Nernst potential for potassium basically specifies the rest of it. The delayed rectifier potassium channels are not very on, and the voltage-activated sodium channels are not very much on, because, after all, we're at something like minus 80 millivolts, so the gates would not be open to any large degree. But if you gave an external stimulus, either from another neuron, or if you have an external human stimulus, you can inject current in such a way that you'll force a little bit of depolarization. So with that little depolarization, you might get to this point, little a here, where now the sodium channels have started to activate a little bit in response to voltage. And because their tau m is so much faster than any of the other taus in the circuit, they'll catch up to these potassium currents, which are basically still in their starting block at that point. At this point, perhaps the current flowing through the sodium channel branch is exactly equal to the potassium channel branch here, so that no net current flows onto or off the plates of the capacitor. In this way, the ddt would be 0. But that's only for an instant, because there's nothing stopping these sodium channels from activating more. So as they activate more, we come up to point B. Now we have more depolarization, and the sodium channels, which activate quickly, are even driven to activate more quickly. So now the sodium channel branch is far outstripping the potassium channel branch, correct? So now the excess current has to flow onto the plates of the capacitor, causing depolarization, more depolarization. So we're going up. The ddt is very positive. But it doesn't last forever, right? Because two things. The sodium channels have a second mechanism, right? Which was inactivation. So their current is limited, although we are very depolarized. And secondly, the potassium channels, they also have voltage activation, right? It's just that they're a little bit slower. Remember, their tau n was about 10 times slower. And because of that, they allow this spike to occur. But now the potassium channels have caught up at point C, such that the current flowing through the sodium channels is exactly equal to the current flowing into the potassium channel block branch here. So at this point, right, there's no current flowing onto or off the plates of the capacitor, so dV/dt is 0. And from that point on, right, the sodium channels inactivate further, and the potassium channels, they're still at a fairly positive voltage. They just activate all the more, and so they win the game. And now the whole circuit is screaming towards the repolarizing.
to action until we return back to the resting state. So I had a few students say, oh, I was studying for MCATs this past summer, and this is kind of the way that I understood action potentials. And it is. And so for a lot of qualitative things, this is a very nice area. The problem is that when you have multiple factors that are contradicting each other, you have no way to really adjudicate. So it's just a he said, she said sort of thing. And so you're left without a much deeper understanding. So before we move on, though, there's a couple things that are sort of good words to define here. So one of the things is there's such thing as called a refractory period. Okay, so you're going to have a lab where you dissect out a sciatic nerve, which is nice, and you get to measure the membrane potential, and then you get to stimulate it with an external stimulus. So when you stimulate it, you're going to get these nice little neuronal actions, something like that. Very nice. But after a while, you stimulate, your group is going to get bored. So, but you have control over the stimulator. So maybe you'll decide to not just use single pulse stimulation, give a train of pulses. Right? So fire away, fire away, fire away. And soon enough, one group will find that if the one pulse comes too close to the other, the second stimulus will fail to stimulate the spike. Okay? And that means that you've invaded a period after the first spike that's too close, and we call that period the refractory period. Like the nerve, the heart cell is no longer capable of firing an action potential. Refractory. Sort of human beings have sort of this sort of thing, right? After a bout of activity, there's a certain period where you just can't do anything more productive, right? So you just have to engage in some kind of recreation, like go to sleep. So that's a refractory period. And it doesn't matter, some student will say, well, maybe we just need to hit it harder. So you turn up the stimulus voltage amplitude, and hit it harder. Nothing will happen. Finally, you'll just burn your preparation. So it's in a refractory period. So that's one sort of concept. But after you wait a while, you stimulate it again, you can fire an action. There's something called a threshold. So as you're trying to stimulate an action potential, and you'll be asked to find the voltage at which you first start to stimulate an action potential in the preparation. So, and you can tell a lot about some personality characteristics of your lab mates when you do this. So some people are very methodical. So you want to find the thresholds. They start with a tiny little pulse and there's nothing there. And then they insist on going up by 0.01%. You do it again and there's nothing. You do it again and there's nothing. And they do it again. Eventually, maybe after 5 minutes of incrementing, you finally get a stimulus. Okay, so that's one very careful kind of person. There's nothing wrong with that. You're going to find that there's a certain voltage at which just above it will fire an action potential. Other groups, some people, they don't have the patience, so they fire first with a very weak one, no response, and then they'll crank it way up, and they'll overshoot the threshold, right? And then they may overshoot so much that you burn your preparation, you can't go any further. So you could do sort of a binary search to find it. Nonetheless, there is one kind of voltage called the threshold. Once you get there, once you stimulate to that point, then the cell itself, the neuron itself, you don't need any external intervention, will go through and evoke an action potential on its own. It's sort of auto-programmed to do that. It's hard to explain these concepts based on a sort of qualitative thing, but we can come to this other way of looking at it that Dennis Noble came up with, which is very clever, and it's a brilliant example of graphical analysis. So graphical analysis tries to give you the intuition of geometry to understand very complicated things. And you need this sometimes, because nowadays with computers you can get a lot of differential equations, a lot of complicated things, and you run the simulation, you see it, but the simulation itself is so complicated that you don't really understand what's going on. The simulation is starting to rival the complexity of life itself. So, and we don't like that, right? I used to debate this with my old PhD professors. What is understanding? Right? Understanding is not just running a simulation that's so complicated you don't know what's going on, right? It's something that you can grasp in your mind and turn over. And sometimes this graph theoretical analysis can help you to achieve that sense of understanding. So here's a very beautiful and simple just taste of that. So our master equation, say for a neuron, is C dV dt is equal to negative the sum of the ionic currents, the sodium and the potassium. If we write it out with our full-bore representation of what's going on, we have, for the sodium current, we have the number of sodium channels, the M gate to the fourth or third, depending on how many gates you want to say are necessary to make the channel open. The H gate, GNA, V minus VNA. This is the current that would flow through a single sodium channel if it were open. And the same sort of formalism, minus the inactivation gate for the potassium channel. So this would be very complicated to understand, because remember, underlying the movements of M, right, are those equations that we covered like in my office hour, right, dm dt, right? So how do you get the evolution of probability? You have to integrate those first order differential equations, which are always in motion, because the voltage, if it changes, it affects the rate constants then changes the rules for how M evolves. So it's all very complexly intertwined. So what Dennis Noble said, though, is, maybe we could simplify it as an approximation. So we could come up with a sort of quasi-instantaneous snapshot of what's going on. That would be a good approximation of how dV/dt would change around a small perturbation, small range of voltages. So here's his reasoning. So he says that, okay, at a given instant of time, H gates, remember they're slow and sluggish, are moving pretty slow compared to the M gates. So let's just, for a little local snapshot around a small increment of time, let's call H a constant. It's just whatever it is. It's not changing that much in that time. And the same thing with the N gates. The N gates, if you remember, are also slower to react to voltage changes than are the M gates. So let's just call N, whatever value it happens to be at, a constant. The only gating parameter which can change at this time then would be the M gates, and they're very fast. So instead of integrating a differential equation, let's just say that the value of M for values of V that move around whatever value we're at this time would be given by the instantaneous steady state value of M. Okay, so M steady state value infinity as a function of voltage. So this is a very good. You change V, M changes, and it changes in a simple way. It follows its instantaneous, the steady state disposition of M with respect to voltage. Okay. Alpha over alpha plus beta. And the only other time variable factors, of course, are the permeation factors, which are very fast. V minus VNA, V minus Vk. So let's then plot what this would look like. So for the potassium channel parts, the N is a constant. The V minus Vk is not. So the potassium current limb would look like this. Just a linear line. Now the sodium channel part, what would it look like? Well, the H gate isn't changing, but remember the M, that's going to activate, and we dissected that, I think, last time we were together. You're going to get this kind of relationship, right? The gates activate, fully activated, then you're just following the battery term here, coming up here. So this would be the sodium channel contribution in this approximation, and then adding them together, the part that would be proportional to dV minus 1 over C times that would be proportional to dV dt. We have to add these two curves together, so you get the dash curve here. So at any instant of time, if we happen to be at this voltage around there, the currents would kind of change this way with respect to voltage. So it's quasi-instantaneous. So what's good about this is that in this framework, there's 3 voltages, 3 points at which the system has a hope of staying still, being fixed. We call them fixed. And those 3 points are the points where dV dt, right, is going to be equal to 0. So where are they? here, here, and here. See that? At those points, this term, which is proportional to dv dt, is equal to 0. So if you just stayed there, things wouldn't change. So we call them fixed points. But not every point, not every fixed point is the same. So there are different kinds. So you can classify them. So let me do it like this. Not quite as good as this one. So this pen has two fixed points. That's one. And we call that stable, because I wave my hand over it, it stays there. Here's another one. It has a hope of staying there, but it's rough. So this one is a fixed point, but it's unstable. So there's the same kind of dichotomy here for these three fixed points. So the fixed points turn out to be zero crossings where the current voltage relation is goes through with a positive slope. Why is it fixed? Just imagine. So suppose you're there, right? And then a little thermal fluctuation makes it so that your voltage increases. So you depolarize, right? So then the current predicted by this little equation will be outward. What does an outward current do? It's positive ions going from inside the cell to outside. It tends to repolarize or drive the voltage back. So will thermal fluctuation come right back. How about if we overshoot? Well, if you go this way, then the current becomes inward. Positive ions going from outside the cell to inside. What does that do? It depolarizes. So then it'll servo control you right back. So you tend to stay right at that fixed point. And here's another fixed point. And what about this one? Here the slope is not positive, but it's negative. So this is like the pen when we try to make it vertical. So if you stay absolutely still there, which I can't, right? If you go a little bit to the right, what happens? Then you have inward current. What does inward current do? That's positive ions going from outside the cell to inside. You depolarize more. That means you're going to go away from that point more, so it's unstable. Suppose I came a little bit on this side. Now I have an outward current, which would tend to make the voltage more negative, so it goes away. So this point, as soon as I leave that tiny point of dv dt equals 0, just by a little bit, I'll either be swept to the left or swept. So this is an unstable fixed point. So we have two stable fixed points and one unstable one. And this is kind of how the cell looks like at rest. So now, what does this have to do with the phenomenon of the action potential? It's very, very nice. So here's your resting potential. That's stable. And what is this? This is the threshold voltage. See that? You could be the lab mate who's very cautious. You can stimulate a little, come up. Every time you come up, you get swept back to the resting potential. Only until you get right up to there, a little bit more than that, and then you'll sweep up here, and then what happens? You go to this fixed point. And what is that fixed point? It's the action potential going on. So if we follow how this now changes, not instantaneously, but through the course of the action potential, we can learn a lot. So here's the original instantaneous current voltage relation. Rest, threshold, and then the ongoing action potential. So you start off here, stimulate very cautiously, you always fall back. As soon as you get one out here, and you're swept up here, now your action potential is underway, you're sort of tracking that. But now that you're depolarized, what's going on? Well, the sodium channels are inactivating, right? And the potassium channels are a little slow, they're activating. So if you add those smaller sodium current and then a growing potassium current, your curve will morph into curve B. Okay, so what's going on there? Well, maybe your action potential will go to a less positive voltage. That's okay. If you continue to go on, the sodium channels inactivate more, the potassium channels activate more. You'll just get to this point of curve C. What happens? You just lost this touching point there. So now how many fixed points are there? One, only this one. So at that point, right, inexorably you're going to end up there, and that means that action potential from that point on, you're refractory. You're just going to repolarize right back to the resting. There's no more threshold points, so no matter how hard you stimulate it, you'll never be able to fire action. And it actually goes back to here. So then, to recover from refractoriness, what do you have to do? The potassium channels quiet down because it's a negative voltage, and the inactivation, because you're at a negative voltage, is relieved, and then you slowly reset back to curve A. Then you're ready to fire action potential. Okay. So this is a very, although you're not integrating the differential equations, you have a lot of understanding of exactly what's going on. This is a taste of graph theory. There are many more grown-up ways of doing it than many mathematical problems, but you're always hoping for some kind of higher ground like this. Okay, so there's a little summary here of what you can get out of electrical signals 3. I'll leave that for the quietude of your own room. And what I would like to do now is to switch into how we actually use compute action potential by numerical integration. So before we get to there, though, we have some way stations. So I want to introduce you to something, a different way of looking at gating, besides the Hodgkin-Hux equation, which is a state diagram view of gating. And then once you have that, I'm going to review for you something that you may have seen. Well, we'll try to make it very simple, the Euler integration method of prosecuting, predicting how a coupled system of ordinary differential equations, even nonlinear, can be computed on a computer to any degree of accuracy you want. And then we'll do a computer simulation of the neuronal action potential. So that's our 3 parts for electrical signals. So, state diagram view of gating. So I'm going to try to recast the mathematics for the Hodgkin-Huxley equation to make it look better. And then, some of you, may say, well, why do engineers care about good looks, right? That's something for, the people in arts and sciences, more for the, more for the aesthetics, the art people, the people in graphic design, things like that. But that's not true. That's not true. Because in science, the beauty of math is that many times when you recast what is known in a more beautiful, compact mathematical representation, that representation points to possibilities that you hadn't imagined even when you were concocting the equation. And then that turns out to be true. And this is going to be good for us in terms of electrical signaling. But it comes up in other realms. So here's a really, really beautiful realm. So way back to physics in freshman year, and we did electricity and magnetism, and here are Maxwell's equations. So they're how electrical fields, E, magnetic fields, B, how they interrelate to each other. And it's really the great work of Maxwell that said that electrical phenomenon and magnetic phenomenon were really one and the same, part of one kind of theory. And this is was my freshman physics professor at the time, Edward Purcell. We had a lot of complicated things, but one of the things that I really remember was when he shared this very beautiful thing here. So there are longhand ways of writing these out, which are really drawn out. And I remember you could look at them. There were old textbooks from the 1800s in the library. And Maxwell's equations didn't look like this at all. They were all drawn out, no vector calculus sort of things. It was all long, drawn out calculus. Very beautiful. But with vector calculus, you could boil it down to something very beautiful here. And looking at something very beautiful here, you'll notice that the electric field and the magnetic field, they behave almost symmetrically as if they're one and the same. They're mirror images, right? It's almost perfect. Except for these two things. Those are the fly and the ointment. And why are these things empty? And the reason they're empty is the same reason that when you have a magnet, right, like the north and the south pole on it, and maybe you always wondered whether you could have a north magnet and a south magnet. So I did this experiment when I was a kid. So I took a hacksaw and cut it in half. But instead of just getting the north half and the south half, each half springs a new south and a new north, so they always come together. So for that very reason, it seemed like there were no such thing as magnetic monopoles. See here, this is an electric charge. We can have positive charge and negative charge. So del dot E is 4 pi the charge density. But there's no such thing as magnetic density. There's no north and there's no south. This is something tantamount to electric current. There's no magnetic monopole current. But wouldn't it be beautiful if there were magnetic monopoles? This is where the dreaming comes in. Like it would be a perfectly symmetrical world. This is where that Paul Dirac actually came up with. This is what it would look like if there were magnetic monopoles. And so what Purcell shared with us is that maybe in your lifetime we'll find them, because it turns out that a lot of times when you recast things very beautifully, it points to a possibility. It's a strange universe we live in. Those possibilities actually are. So I point you to this paper, just published in January 2014, published in the journal Nature, and here they finally observed monopoles right here in the lab. So here's an example where beauty counts. So where is this beauty going to come in here? It's another way of representing gating in the following way. So if you remember, say our delayed rectifier potassium channel, right? It has 4 N gates, each of which can be disabled or enabled, right? So I could maybe represent the state of a potassium channel by this little cigar with 4 numbers. So here's one where all 4 of the N gates are disabled. 0, 0, 0, 0. That would be one state. Over here is the only conducting state where all the gates are enabled. 1, 1, 1, 1. But in reality, these are only 2 of 16 possible states, right? So here in this second column, we have states 2, 3, 4, 5. What's common in all of these is that only one of the gates is enabled, all the others are not. Okay, but we can denote which of the gates is enabled, and that makes it special. And there's, by one single change, you can go from 1 to 2, 1 to 3, 1 to 4, and 1 to 5. And those are the only changes by one thing changing that you can do in terms of transforming state 1. Likewise, by changing only one thing in terms of the disablement, all of these can only go back to 1. You can go to this column here where what's common about this column is that 2 of the gates are enabled in different combinations. And their possibilities of connectiveness by changing one thing are shown by these lines. And so forth. We're here where they're all 3. So this is called a state diagram view. And what's beautiful about this is that in this sort of formalism, we don't have to assume that all the gates are identical. These gates are known by name. They can have different rules. And they don't have to be independent. Having one guy enabled could change the rules for how a second guy would get enabled. And we can capture that by having different rate constants for each of the transitions. So this is a much more complex sort of formalism for looking at it. Okay. And it has a really nice way that you can represent it in matrix. So what I could do is now represent the system in terms of what we call a state vector. And this is a vector, once you know it, you know everything about the system. So it's kind of nice, right? You don't have to remember too many things. If I have a state vector, then there's nothing else to know about the state. You know, like when the president gives the State of the Union, all you have to do is the state vector of the country, and that's it. You don't have to listen to the rest of the whole sort of, presentation. So what is the state vector? It's the probability at an instant of time that I'm occupying state 1, the probability that I'm occupying state 2, all the way to the probability that I'm occupying state 16. And the beauty of the system is that all of its motion is encapsulated in this single matrix equation. So d by dt of the state vector, what this really means is that dp1 dt, dp2 dt, we just bring that operator in here on all of them, is equal to this matrix called the T matrix, which is really just careful bookkeeping about the rate constants, times the state vector of the present time. So if I call this P like vector P, and this vector P, and this Q, dp dt is equal to qp. So this seems very sort of maybe abstract at the moment, so let me break it down. So to break it down in the simplest way, let's assume that all the gates are identical and independent. And it turns out that all of this gamish collapses down into these 5 states here with rate constants like that. You can kind of go through that. Happy to go through it in office hour, but I bet you can get it just in the quietude of your own room. 4 alpha because there's 4 gates that can enable 1 beta because any one will bring you back, and so forth. Now, how would we write this in state vector form? Very simply. So the PDT right here is QP. And let's just take the reasoning through. So how would the time derivative of being in state 0 turn out to be? Well, we know what it has to be. It should be minus 4 alpha times the probability of being here. So minus 4 alpha times the probability of being there. Plus beta times the probability of being in state 1. Beta times this probability. And then whether I'm in any of these, it really doesn't affect the time derivative of being. So you see the 0, 0, 0. And we could prosecute this through for all of these other guys here. So it's beautiful. Some of you might think it's not beautiful, but what does it really tell us? A lot. So one of the things is, this looks complicated, but that looks very simple. And the whole thing is that much as many of us think we can multitask, the human mind can really think about only one thing well. You might think you could do it, but you really can't. If you're really thinking at your best, you think about one thing. So we know that there are many states in any kind of system, but the beauty of matrices is that it keeps track of all the interactions. But for us, in manipulating in our mind, we can treat it as if it's one thing. So that's a lot of anxiety relief. It's also a lot of clarification of your thinking. That's why people have spent a lot of time on matrix analysis. But that's really it. It's not to torture you. It's actually anxiety relief. It's clarifying the logic to its essence. So what does this buy us? Okay. Well, one thing is that by simplicity, very beautiful simplicity, and it's going to point us to an exact way that we can use Euler integration on any state, any size system. So that's one. Second thing is that, although we won't go into it, it points to a simple way of simulating a single molecule called stochastic simulation. And just to remind you about that,
by taking advantage of that, we can simulate the sodium channel. And so we're just simulating of a single sodium channel and calculating the average. And it becomes also very simple to do it once you cast a system like that into the state vector formalism. And the third thing that's really beautiful, spouting how this focuses, clarifies your thinking about very complicated systems, is it points to the analytic solution, very simple analytic solution to a very complicated system. So, let me turn the light on. So, this system looks pretty nice and simple. In fact, I told you that you should completely know this for a scalar function, right? It's one thing that you should know completely. And this looks like the scalar function, except that we bolded it here. The bold means that it's really a vector, and it's really a matrix. So it's a little complexity there, but if you just rest that aside, right, it's very comfortable. It fits in the palm of your hand. It's kind of like the early iPhone. So beautiful. Just the balance is perfect, right? It's all rounded and all of that. Now you can't do it. So, but if I gave you this function, where Q is a constant, and I give you the initial condition, some known value, right? We know what the solution for that is, right? Okay, got that? That's very beautiful. So then, because the laws of algebra and arithmetic are very much the same for matrices and vectors as they are for scalars, it turns out that the solution to this, the analytic solution, is just that. It's the matrix exponential. So you might be asking, what is the matrix exponential? Well, what the late Jack Roux, the professor of electrical engineering, did. This is the most beautiful function in all of applied mathematics. Arguably it is so. But what is it? And I remember as an early graduate student doing it, and I was playing with Mathematica and had real problems like that, and gave it the Q matrix, and it said the solution was P of t equal to, and in symbolic terms, the matrix exponential, just like that. But it didn't tell me what it was, so it's incredibly frustrating. So, well, what is e to the x? One way of determining it, right, is its series definition. So because the laws of algebra work out, what is the matrix exponential? It's this. The identity matrix plus qt plus t squared over 2 factorial. So by boiling down any system into this with the matrices, right, we can write down the analytic solution just as simply and beautifully as if we were just dealing with a scalar function. So that's incredibly powerful. Incredibly powerful. Isn't that cool? Really? Yeah. It's like a Presbyterian. So, what if the system's nonlinear? Well, we can't really use that. So then we have to use this numerical integration. And numerical integration is a really beautiful thing that man started to play around with in the late 1600s when they're trying to calculate orbits. And then there was calculus and then there was Newton. But there might not be an analytic solution, so they started to do these sort of arithmetic calculations to calculate the solutions to differential equations. And so my first exposure to this was in graduate school, and I met a that's it. So right. So let me know if you can't see this. So they have a really good applied math and physics program at Cornell University. So from a graduate student friend of mine who was from that program and knew a lot of stuff and wasn't embarrassed to show that he knew a lot of stuff. So we're talking, and he said, I have a way where just by a spreadsheet and arithmetic, I can solve any differential equation. I said, oh, that can't be true because I spent a lot of time tortured with a lot of papers, doing differential equations, things like that. So I tried to come up with a problem, but honest to goodness, I couldn't remember any diffie at the time. So the only one that I could remember was this one. So said, dp equal to minus kp. So I didn't know to make it a cubic. So I knew that the solution to that, say that p0 is just 1, I knew the solution would be e to the minus. So I said, let's see you solve that. So yeah, it seemed pretty good. So I said, okay, the way I'll do it is the following. I know that your initial condition is 1. You gave me that. I said, okay. So what if I step a little bit into the future? Wouldn't that be approximately equal to 1 dp dt times delta t? Yeah, that's true. And what's dp dt? Well, that would be minus k times 1, the value that it was at delta t. So that would give me into the future, right? And then what if I jumped a little bit ahead into the future? Well, wouldn't that just be whatever I calculated that to be plus dp at delta t dt times dt, and I could just sort of march into the future. And I said, yeah, that's true, but as soon as you go too many steps, right, it's only an approximation, I'll be far off, and it won't help at all, right? This is just kind of a mind game. He says, no. This guy, Kepler kind of, they show that it converges, and you'll never be that far off. So here's the actual calculation. So we have, if you look here, we have time in this column. Here's time in this column, right? And here's my initial conditions. Okay. And here's my analytic solution. Here's my analytic solution, sorry. And we just calculate the solution e to the minus kt. Here's my initial condition. Here's my little algebraic sort of equation marching into the future, right? And then the algebraic little calculation is in red here, the analytic solution is in black. So if we just copy this formula, propagate this algorithm, right, what do we see? follows almost perfectly. That is true. As long as your delta t is small enough, the errors won't grow infinitely. Just stay very close. If you want a better answer, you use a smaller delta t. So that was his claim. So I said, wow, that's kind of neat, but it's a pretty easy problem. So tried to come up with a different kind of question, and by this time I was thinking a little bit. And which one is it going to be? Is it this one? So, maybe this one. No. Here we go. So let me return to my PowerPoint. So this one, is that full? So I kind of remember this problem. Classic one from physics. So a little mass here, a little spring, a little dash pod in the presence of gravity hanging. So equations of motion for this, right? We can do this. So the force on this mass, the net force is equal to the mass times the acceleration, which would be m, the second derivative of x with respect to t. And so what is that force? Drawn in this way, defined in this way, it would be that of the spring minus the spring constant, v0, times x, minus gravitational force minus mg. And then the dash pod minus f dx dt. Okay? Right. And the dash pod, if you think about it, right, is a mechanical version of a passive aggressive person. So if you have no velocity, it doesn't resist. The minute you try to do something, it resists. Oh, not resisting the minute you try to do something. Try to do something else, something that opposes you there. So this is the dash pod. So I said, okay, can you integrate this differential equation, right, so that we could solve for x? And I knew it was kind of complicated. And I said, there's no way you can do it because the sort of system that you showed me for this first problem, I had to have something like dx dt. There was no higher order second derivatives and third derivatives. He says, no. I can do it. And so he said, let's make the following sort of substitution. So let me define two variables. Let x1 be x, and let x2 be dx dt. Okay? So, and then let me write the equations now as this. dx1 dt is x2, and dx2 dt is equal to the sum of force terms. That's great. And then, because I like beauty, we'll put it into this state vector form. Okay, so we have d by dt x1, x2. It's equal to q times x plus this little added term. All right. So essentially we have dx dt is equal to qx plus g. And this is only one matrix differential equation, and now we got it as a first derivative. So now you can kind of see how we could use this Euler integration, even though the system has two equations, or was originally second order. So x0 is given. X of delta t would just be where we started, plus dx0 dt times delta t. We can make a substitution. dx0 dt by our equation is qx0 plus g. X of 2 delta t, just march into the future all the way down to here. So it's just arithmetic now, just arithmetic. So does this really work? And let's take a look. So that's what's in the simulation here. So I can't see on the line. Okay. I need a little bit more. You should speak to the president of Hopkins. Whoever designed these things, they never tried to teach. Serious. So we have time in this side. Okay, time, right? We have our variables up here. Spring constant, the mass, gravitational constant, things like that. And what do we have here?
Well, we have the initial values of x1 and x2. And what do we have down here? We have those arithmetic rules for how you calculate the new values of x1 and the new values of x2 simply based on arithmetic performed on the previous values, okay? And then now we're just going to propagate this. And we're going to plot the outcome on the graph on the right. So this accords very much with your intuition, right? So we started here with zero velocity. You let go of the mass, and what does it do? And then it settles down, right? Isn't that great? I didn't have to do any kind of analytic or anything. I'm just doing arithmetic on this. This is the power of Euler integration. Let's change a few things here. Like, okay, okay, so here's the dash pot, the passive aggressive element. So what if I increased it, to like 3? Oh wow, you can see the effect of that. So passive aggressive people, they have their purpose. They, instead of getting a little crazy, right? They can slow it down like molasses. You have a smooth approach to there. And then probably with Dr. Sarma, you talked about critical damping and things like that. So we could pick a value where you don't tame all the wildness. You get a fairly good approach. Well, that's too much. Maybe 1.7, right? Where you just have the fastest you can go without overshooting. And we're getting this just by calculations on arithmetic. So I was pretty impressed by this. Yeah, and you should be too. So here now. So at this point, I think all of you are very bright. You can see that for any kind of differential equation, I could break it up into a matrix state vector equation, and I could integrate it. So basically, your differential equation class is, this is it. You could solve almost anything. Now, the way we're doing it is sort of a numerically inefficient way, but it's conceptually very simple. But all the advances are just fancy ways to get it so that you can prosecute it more accurately, more quickly, more feasibly. So you'll have to take a course in numerical analysis to get into that. But now you know why that would be good. Okay, so now, reviewing some of the key properties of the Euler algorithm. So as delta t becomes very small, calculated values become more exact. Errors do not accumulate. They don't build up forever. They'll stay within certain bounds as long as delta t is sufficiently small. And the other thing, which I didn't show, if your delta t is too large, it's very obvious. Your solution will blow up. So if it blows up, just shrink your delta t. And so for very complicated problems now, sometimes, because computational power is so good and so cheap, instead of getting a fancier algorithm, we just shrink the delta t way down and let the computer do it. And they're usually very, very good. Okay. So now I'm going to apply this to the action potential. So let's go ahead with this. So, cheat sheet. So, how can we do this? Well, dn dt for the end gate on the potassium channel, that's from time 0, it would be just given by this first order equation, right? Alpha voltage at time 0, 1 minus n minus beta, the value of the voltage at time 0 times n0. And the way we set alpha and beta are these exponential functions, instantaneous functions of voltage, right? So this is stuff that we already have gone through. So to march into the future, approximately, n time delta t would be n at time 0, dn dt at the derivative at time 0, delta t. And I know what that is. It's just this, so you just plug it in. And that should march us forward into time. How about for the m gate? Same thing, dm dt at 0, this little first order module, this instantaneous function of voltage exponential. And we could march into the future, m0 plus dm dt at time 0, which is this. times delta t. Okay. How about the h gate for an activation? Well, this is one of the previous lectures. Instantaneous function of voltage. To march ahead in the future, h delta t is h0 plus dh dt delta t. But dh dt, oh, we already had it. So we could march into the future. And what about voltage? dv dt is the value negative the sum of the ionic currents at time 0 divided by the capacitance. And what are these currents? Well, remember, they are just combinations of the M and H parameter and the N parameter. So we could march forward. Vm delta t in the future would be Vm at 0 plus dv dt at time 0 delta t. But what is that? That's just negative the sum of the ionic currents over C. And I can calculate all that from M, H, N, V0 values. Right? So it's just arithmetic, and I march forward into the future. So if I put it into vector form, all these sort of state variables, dx dt is equal to qx plus gx. So this is a slightly different form, but not very different. Notice that the Q matrix, the rate constants, they're a function of the value of some of the members of the state vector, namely voltage. So this Q matrix is changing, but it really doesn't change our algorithm whatsoever as we march into the future. We just do this arithmetic. We start with the one value, we march by arithmetic, delta t into the future. We plug that value into here. We march another, now 2 delta t in the future. We keep doing this. And as long as the system is convergent, we predict how the action potential evolves as accurately as we want to. Okay, so the first time this was done, the first conception of this was in around 50 or 52 in a classic paper by Hodgkin and Huxley. And they had a computer to do this on. They were in England and they had a computer left over from cracking codes in World War II. But it was down for the winter and it wasn't going to be fixed. So Alan Hodgkin said to his graduate student, Andrew Huxley, said, something like, Andrew, we can't wait all winter. Why don't we do it by hand? So he did the numerical integration by a hand calculating machine, row by row, very easily, and they had beautiful simulations. It took them a couple of weeks, but they did it. But we don't have to do it. We can do it in a spreadsheet. Oh, hey, do I have some slides? Yeah, let me see. Okay, yeah. So this is clunky in a way to do it by a spreadsheet, but it's very beautiful in a way too, because although you could use a more sophisticated way like MATLAB to solve it and use the ODE solver, you don't really understand how it's doing it, right? You feed it an input thing and you get an output. This thing you feel every step, row by row, the way the algorithm's really working, and then you can understand it. So as my physics teacher in high school said, I like Cartesian coordinates where the x, y, and z coordinates are like rods in space and you have to step over them. None of this sort of curvilinear space-time physics. So this is kind of that. You have to step over the axes. They're very real, but you understand. So basically, row by row is time over here. The state variables are the different columns. There's a little scratch area that you can work with. There's a graphical area, and then here's our parameters. And basically, what you have to, these are the state variables. And what the key thing for this to work is based on known quantities, state variables at time 0, I have an algorithm that allows me to completely specify the new value of the state variables, delta t in the future. And then I can rearm and do it the next row and the next row. That's the key thing. Okay, so we're going to try to test these things. So let me just write these out. So VK 0, 140, and 70, 30, 20. Okay. So I'm just going to lead you through a fanciful thing, and all of these are up on. What you'll get out of these is that you can really play with it.
So, here we go. So, I've just zoomed in here so we have the graphs. We have some of our parameters over here. And here's just a smidgen of the time, the voltage, and then the state variables would be over here. But each row is just calculated based on values in the previous row, and it just propagates them, just like we did for the spring calculation. Are you with me? So let's see how these have the default parameters, and the way you fire an action potential is you just come over here, and let's give a stimulus to something a little above the threshold. Let's say minus 54 millivolts. And so we have a neuronal action potential, kind of. Stimulus pulse, sharp spike, and it comes down. So that's very beautiful. And you can see the IK and the INA. You can see the gating parameters. These are all part of the simulation. So if you ask me what the analytic solution is, there is no analytic solution because it's very, very nonlinear. But we can simulate it very beautifully. So let's see if this can tell us a few things here. So you can play with this. So the first thing that I told you about earlier in this is like if you add a high extracellular potassium, we could silence the heart. And so too we could silence the brain at the same time. You'd have to be careful about that. So if I added high potassium, maybe I would make the Nernst potential, EK, go towards 0. So if I do that, okay, you get one action potential and then that's it. Your brain is quiet as so this would be a way of silencing your brain and your body. Let's go back. Let's try another sort of thing. Let's work on the sodium channels here. So I like to imagine myself in a sushi bar, Japan, pufferfish. I've actually had this once. I went over, was invited to a scientific conference in Okazaki, and they're such wonderful hosts, really. I always feel bad because I could never be as good a host over here, but it was wonderful. So we had wonderful science during the day, and then they took us to a real Japanese sushi bar, and it was fantastic. There was a sushi chef there. We could order pufferfish, and there were a lot of good drinks too. Very high octane, so that added to the experience. So the thing about the pufferfish that is good, it's pretty good. It tastes really good. It's very, but there's also a psychological element because they have an organ that contains tetrodotoxin, which is a very powerful toxin. When it binds, it makes the sodium channels unable to open, so it knocks them out. So it's lethal. That's how the pufferfish hunts for its prey. Inject some of that into a prey and fly over and then just eat it. So this is great, but a good sushi chef that's licensed has to clean that out very carefully so that you don't want to eat tetrodotoxin. But the idea is that maybe there's a little bit. So as you're enjoying it with the high octane drinks, your mouth tingles a little bit. So suppose your sushi chef has sort of a bad day, a little bit of a bad day, and doesn't quite clean things out there. So maybe your sodium channels get knocked out a little bit. So instead of being at 140, right, in terms of their conductance, it goes down to something like 30. Oh, so now you're feeling woozy because there's a delay to the peak of your action potential, right? And then if you imbibe a little bit more, right, oh, it could be really bad. So now you're unconscious here. So, and then your sushi chef is usually serving you at the same time, so they're attentive, and he goes, oh, I know what's going on, so this is really bad. So they bring out the cold water and make you drink this profusely and pee a little bit, pee it out of your body, and then it's nice. You return back to normal. And then, maybe he says, oh, I'm so very sorry, and then you probably don't know, you don't feel that bad. I mean, he brought you back very quickly. He says, let me make it up to you. I'm going to give you some of my best Japanese tea to make it up to you. So you take a little bit of drink of this, and instead of 70 all of a sudden, this becomes 30. Okay, so now your action potentials are longer. Maybe you have a heightened sense of consciousness. Oh, this tea is incredible, right? But then you take a little bit more of it, and then
Now you have hallucinations. and you realize what's going on. It wasn't tea, the leafy kind. It was tea, the kind that you might have been reading in Johnson and Wu. Tetraethylammonium, classic blocker of potassium channels. That's why our potassium channels are going down. So the way to get this really with the simulation is to look at it and see if you can dissect it a little bit more than I can do. This is a really nice sort of thing here. So let me turn here. But isn't that powerful? All I did was just arithmetic, calculate it, right? And now we have even a spreadsheet. That's the amazing thing. People, I had summer students from Jiao Tong University and said, we used Excel before, but we didn't realize you could do all this stuff. Even in a spreadsheet, you could do a lot. So there's a lot of important points that we came to hear. One of them is, you should know about state diagram mechanisms and how to write them. It's a really good thing. You should know 3 advantages of the state diagram view, which were good. You should understand Euler integration for solving a couple of differential equations. Like when you come out of Hawkins DME, if you know this, then you learn something very important. This is a very, very useful sort of thing. And it'd be good to be able to pseudocode the Adhucs as if you were coding it a little bit yourself. So let me wrap up. We have just a little time here. So this is the end of your electrical signals part. You're moving on to the contraction part, and so the electrical will feed into the motion. But what I think I wanted to leave you with is a sense of wonder about the construction of biological life and the universe. And I got this sense once when my kids were a bit younger, and we were visiting a lake high out in New Zealand. That sense of wonder. So how is it that this language of electrical signals that really governs every aspect of biological life, how can it be so complex and yet so economical in its implementation? How did it ever come to be? It's just amazing. And then the other thing that's amazing is that as we thought about it, right, with electrical circuits, we did circuit analysis, we thought about the chemical reactions, brought thermodynamics, we could find a kind of logic behind it, as complex as it was. And so there's sort of like a deep order. A lot of it is mathematical, a lot of it is physics that holds incredible sway over not only biology and engineering, but just about every realm of human endeavor. It didn't have to be that way, but somehow it is. Somehow these ways of thinking are sort of like the magic of Harry Potter, and we are sort of endeavoring to be the wizards. And that's going to serve you well if you try to mind that both in this course and beyond. And here's just an idea of some of that wonder. So here's what we understand how the universe came to be. So here's the Big Bang, 14 billion years ago. And here's how long there's been life on Earth, about 3.8 billion years. And where do we come in? Homo sapiens sapiens. Just a fraction, right? Just a fraction. And then underlying all of this are a series of master equations. So for the Big Bang, somehow energy and matter, mass, came into being out of nothing. That's the implication of the Big Bang. It doesn't make any sense to ask what happened before. It's a non sequitur because time had its existence at the Big Bang. There's no before. Here's another master equation from our course. is equal to minus 1 over c, the sum of the ionic channels. And here's another awesome equation, the Friedmann-Lemaitre equation from general relativity, which explains the stretching forward for the coordinates of space-time, this envelope getting bigger as we get out from the Big Bang to where we are today. So where did these come from? Why do they hold so much sway? Very powerful. So with that, I'll give you continued success in SBE1, and you're officially launched from electrical signals. Thank you very much.